Okay, let's start answering the mystery questions about the interference of light. Question number 1. Which of the following must be true for two waves with identical amplitudes and wavelengths to undergo complete destructive interference? Complete destructive interference. So, to produce a complete destructive interference, when one wave is crushed, other wave must be trough. So in this case, these two waves can cancel each other. What does it mean? The angle between them must be 180 degrees. One of them is, as you see, in positive y direction displacement. The other one is in negative y direction. So angle between these two vectors is 180. So the waves must be 180 degrees out of phase at all times. C is the correct answer. Coherence is the correlation between the phases of two or more waves when the waves have the same wavelength and preserve. Coherence is about the constant phase difference. So phase difference mustn't change as time passes between two sources. Then we can say that these two sources are coherent. So constant phase difference is the answer in here. Question number 3. What is the necessary condition for a path length difference between two waves that interfere destructively? Destructive interference. So an odd integral number of half a wavelength. So odd integral number means lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2. So always we have 0.5 lambda, which provides the destructive interference. So this is the correct answer. But integral number of wavelengths means 1 lambda, 2 lambda, 3 lambda. This is conditioned for constructive interference, not destructive. Odd integral number of wavelengths, 1 lambda, 3 lambda, 5 lambda. This also provides constructive interference. This because if the wavelength is multiple number of wavelengths, if the path length difference is multiple number of wavelengths, it's constructive interference. It doesn't matter odd integral number of wavelength or even integral number of wavelength, which is 2 lambda, 4 lambda, 6 lambda. C and D both produces constructive interference. B is the complete condition for constructive interference. So A is the correct answer. Odd integral number of half wavelengths, which means lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, and so on. So they produces destructive interference. Question number 4. In an interference pattern, if the path difference between two waves is 3 lambda over 2, the fringe appears on the viewing screen. So this is destructive interference because lambda over 2, if it is lambda over 2, 1 lambda over 2, 3 lambda over 2, 5 lambda over 2, 7, it's the destructive interference and dark fringe. But which one? Path length difference starts for dark fringes from lambda over 2. So lambda over 2 for the first dark fringe. Next one is 3 lambda over 2 for the second dark fringe. Next one is 5 lambda over 2. It goes on by the odd integral number of half wavelength. So this is first dark, this is for second dark, this is for third dark. It goes on this way. So answer is second order dark. Because of their great distance from the sun, stars are essentially point source of light. When you look at the stars, you see them just like points. But if the two stars were near each other in the sky, the light from them would not produce an interference pattern because light sources are incoherent. So two independent light sources produce incoherent waves, and that's why these waves cannot produce an interference pattern. So not coherent is the correct answer. Not coherent is incorrect, because if it is coherent, you should observe interference pattern. The phase difference between them is constant. This is also definition of being coherent, so this is not correct. So only answer in here is correct, is would not produce interference because of the light of the two sources, light of the two stars is not coherent. So A is the correct answer. Question number 6. The difference in the distance traveled by two beams when they are scattered in the same direction from different points. This is path difference, definition of the path difference in the book. You can check it. So there are two sources, and these two sources produce interference pattern depending on the difference between the distance traveled by the waves, which is called path difference. Question number 7. In interference pattern, if the path difference in angle between two waves is 3 pi radian. So this is remember, for constructive and destructive interference, for constructive interference path length difference was 0, lambda, 2 lambda, 3 lambda. This is for constructive interference, and each wavelength corresponds to an angle which is 2 pi radian, because one complete wave has an angle which is 0, pi, and 2 pi radian. One complete wave forms when the wave propagates or vibrates by an angle of 2 pi radian. So every 1 lambda corresponds to 2 pi radian. So 2 times 2 pi 4 pi, 3 times 2 pi 6 pi. As you see, for constructive interference, phase angle difference between two sources must be 0, 2 pi, 4 pi, 6 pi, 8 pi, which is the even integer of pi. But for dark fringes or destructive interference, 0, lambda over 2, 3 lambda over 2, 5 lambda over 2, and so on. So if instead of each lambda you write 2 pi, so it becomes 0 pi, 3 pi, 5 pi, 7 pi. It goes on this way. This is for destructive interference. For destructive interference, path length difference, according to path length difference, you can define destructive interference, which is dark fringes, 0, lambda over 2, 3 lambda over 2, 5 lambda over 2 is the path length difference. And also you can define the fringes at which dark destructive interference occurs, or dark fringes, according to the phase angle difference, path difference in angle, 0, pi, 3 pi, and 0. 0 does not exist by the time 0 is for the center. Center is the bright always. So this is for the first dark, pi is for the first dark, 3 pi was the second dark, 5 pi is for the third dark, 7 pi for the fourth dark, and so on. It goes on this way. So that's why 3 pi is second dark. Instead of lambda, you are going to write 2 pi. When you write 2 pi, you will get the answer is 3 pi. The correlation between the phases of two or more waves, this definition of the coherence. Definition of the coherence. What is the necessary condition for path length difference between the two waves interfere constructively? An odd integral number of half wavelength, this is the condition for destructive interference, which is lambda over 2, 3 lambda over 2, 5 lambda over 2. This is for destructive, not constructive. An integral number of wavelengths, yes, this is lambda, 2 lambda, 3 lambda, this is correct. 4 lambda, and when the path length difference is multiple number, integral number of wavelengths, when the waves arrive on the screen, they are in phase, so they form constructive interference. This is correct answer. C and D also provides, but not complete, odd number of wavelengths, lambda, 3 lambda, 5 lambda. This also provides for constructive interference, but not all the conditions. The first one only talks about 1, 3, 5. D only talks about 2 lambda, 4 lambda, 6 lambda. Yani C talks about half of the correct answer. D talks about half of the constructive interference. That's why not complete, but B is talking about all conditions for constructive interference. So D is the correct answer, the most correct answer in here. And let's continue with some problems about the destructive interference. In the equations of the interference, what does the term d represent? Remember, the sine theta is equal to m times lambda, or m plus 1 over 2 lambda, depending on the constructive and destructive interference. This d represents the separation between the sources, the distance from the midpoint between the two slits. No, not this one. Distance between the two slits through which the light passes. This is correct answer. Distance between two slits through which light. This is correct answer. Distance between two bright interference fringes. No. Distance between two dark. No. So this is the correct answer in here. If a double slit experiment were performed underwater, how would the observed interference pattern be affected, and why? When light enters from air to water, in the 10th grade, we learned that speed of the light decreases. When light enters from air to water, its speed decreases. So V decreases because frequency of a wave does not change. Its frequency of light does not change. If speed decreases, wavelength also decreases when the light passes from air to water. If wavelength decreases, what happens to the fringes? According to the equation of sine theta, m lambda divided by d. As lambda gets smaller, theta also gets smaller. What does it mean? The fringes get closer to each other, so it becomes narrower and narrower. Because it getting narrow, talking about the decrease, it would decrease because lambda gets shorter in water. So A is the correct answer in here. If a double-slit interference experiment were performed for the light rays with different colors, blue, red, orange, and yellow, angular displacement for which is larger? Again, use the equation of sine theta, m lambda over d. The light which has the longest wavelength will have the widest, largest interference angular displacement. Of course, we know that the red has the longest wavelength in this lights, blue, red, orange, and yellow. Of course, if the red has the longest wavelength, so it must have the greatest, largest angular displacement. Theta C is the correct answer. Question number 4. Which of the following expression correctly describes the condition for observing the first dark fringe in interference pattern? First dark fringe occurs when path length difference is lambda over 2, and when the sine theta is equal to lambda over 2, first dark fringe appears on the screen. The distance between two slits is 0.03 millimeter. The second order bright fringe is measured at the waving screen at an angle of theta from the central maximum. Sine theta is 0.037. Determine the wavelength of the light. So we know d sine theta is equal to m times lambda. In here we will calculate lambda. That's why we should divide both sides by m and simplify m. Lambda is going to be d sine theta divided by m. D is given in millimeter, 0.03 millimeter, but we should get the answer is in nanometer. From meter to nanometer, we should multiply by 10 to the power of 9, but from millimeter to nanometer, we have to multiply millimeter by 10 to the power of 6. So 0.3 times 10 to the power of 6 nanometer is D. The sine theta is given as 0.037 divided by m. It is the second order. M is equal to second order bright fringe. So we are going to use the calculator. 0.03 times 10 to the power of 6 times 0.037 divided by 2. Answer is 555. Lambda is 555 nanometer. And question number 6. A beam containing light of wavelengths lambda 1 and lambda 2 passes through a set of parallel slits. In interference pattern, the fourth bright line of the lambda 1 occurs at the same position as the fifth bright line of lambda 2. If lambda 1 is 540, what is lambda 2? First, both light passes through the same set of parallel slit. What does it mean? D is the same for both color, and also they have the same position. What does it mean? Thetas are the same. If these are the same, thetas are the same. D times sine thetas are the same for both color. Same. If these times sine theta is the same, m times lambda other side of the equation also must be the same for color. What does it mean? m1 times lambda 1 and m2 times lambda 2 must be equal to each other because their positions are the same. Their slit separations are the same for both colors. Then after that you are going to write m1. m1 is fourth bright line of lambda 1. 4 times lambda 1, lambda is 500 and lambda 1 is 540 is equal to, has the same position of the fifth bright fringe of lambda. To calculate lambda 2 is the question. So divide both sides by 5, you will get the correct answer. So when we divide them by 5, we will get the answer. I think 432 is the answer. Let's calculate once again. 4 times 540 divided by 5. Answers, yes, 432 nanometer is the correct answer. Monochromatic infrared waves with a wavelength of 750 nanometer, so lambda is given, pass through two narrow slits. If the slits are 25 micrometer apart, so this is micrometer, yes, T. At what angle approximately will the fourth order bright fringe appear on the viewing screen? So fourth order bright, so m is equal to 4. So theta is the question. At what angle? Theta is the question. I'm going to use the equation. D sine theta is equal to m lambda. We know that. So theta sine theta is equal to m lambda divided by d. Then theta is going to be sine inverse in bracket m lambda divided by d. Okay, let's calculate it. Sine inverse in bracket. M is the second or fourth order bright fringe 4. Lambda is 750 nanometer, but we have to convert all the lengths to the meter, 10 to the power of negative 9 nanometer to meter, divided by D is 25 micrometer, 25 times 10 to the power of negative 6. Every micrometer is 10 to the power of negative 6 meters. So I'm going to use a calculator now. So shift sine, which is sine inverse, bracket, 4 times 750 times 10 to the power of negative 9 divided by one more bracket, 25 times 10 to the power of negative 6, close the bracket, once again close the bracket. Answer is 6.9 degrees. So theta is 6.9 degrees, which is A. Question number 8. The distance between two slits is 3 micrometer. The second order bright fringe is measured at the viewing screen at an angle of theta from the central maximum. Sine theta is 0.037. Determine the wavelength of the light. Okay, this is very similar to question number 5, but there is a slight difference. Okay, distance between two slits are given. This time we will calculate the wavelength. Again, we will use the wavelength equation. Wavelength equation for bright fringe is d sine theta divided by m. D is 30 micrometer. 30 micrometer, let's convert it to meter, 10 to the power of negative 6 meter, times sine theta 0.037 divided by m. M is the second order bright fringe 2. So let's use the calculator. 30 times 10 to the power of negative 6 times 0.037 divided by 2. It is 5.55 times 10 to the power of negative 7 meter. So we have to convert meter to nanometer by multiplying 10 to the power of 9. 555 times 10 to the power of negative 7 times 10 to the power of 9 nanometer. Result is going to be 555 nanometer. So B is the correct answer. Which of the following expression correctly describes the condition for observing the fourth dark fringe in an interference pattern? Remember, interference pattern, first the dark fringe starts from first dark fringe lambda over 2, next dark fringe 3 lambda over 2, next one is 5 lambda over 2. It goes on the odd number of half wavelengths. 7 lambda over 2, it goes on like this, 9 lambda over 2, and so on. First dark fringe is lambda over 2, second dark fringe is 3 lambda over 2, third one is 5 lambda over 2, fourth one is 7 lambda over 2. It's the fourth dark fringe, so 7 lambda over 2, D is the correct answer. Which of the following expression correctly describes the condition for observing the central bright fringe? Central bright fringe path length difference is 0. D sine theta is 0. This answer is going to be A in here. So one more problem we added. Now let's solve this problem as well. Light falls on a double slit with a slit separation of 2.02 times 10 to the power of 6 meters. D is given, this is D. And the first bright fringe is seen at an angle of 16.5, which is theta. Find a wavelength of the light. Again, we will use this. Lambda is equal to D sine theta divided by M. D is 2.02 times 10 to the power of negative 6 meter. Sine theta is given as 0.284 divided by, it's the first bright fringe, which is 1. Then let's use the calculator. 2.02 times 10 to the power of negative 6 times 0.284. Answer is 5.74 times 10 to the power of negative 7 meter. To convert meter to nanometer, we should multiply it by 10 to the power of 9. So multiply it by 10 to the power of 9. Result is going to be 574 nanometer is the answer, is the correct answer in here.